This is the final video of the semester on the second part of Chapter 16. This video covers directing groups, reactivity of benzene derivatives, nucleophilic aromatic substitution, elimination addition, and oxidation and bromination of alkyl side chains. As we discussed earlier, there are ortho, meta, and pair positions on the benzene ring relative to a group. So if we already have a group on the benzene ring and we want to do an electrophilic aromatic substitution, where do we put that incoming substituent? Do we put it in the ortho position, the meta position, or the para position? Well, it depends on the nature of the group already on the benzene ring. Some are what are called ortho-para directors, which means they will direct the incoming substituent to the ortho and para positions, which means you will get two products, one where the incoming substituent is at the ortho position and one where the incoming substituent is at the para position. And these are typically donating groups, and you can identify them because they are either alkyl groups or they have a lone pair on the atom directly bonded to the benzene ring. So these are examples of ortho-para directors. So if we take toluene, methylbenzene, and we do a nitration reaction, so we're using HNO3 and H2SO4, we get primarily two products, the ortho and para products. We get so little of the meta, we can really just ignore it. So an alkyl group is an ortho-para director. Here's another example. So here the OCH3 group is an ortho-para director. Notice that the atom directly bonded to the ring has lone pairs. That is a giveaway that you have an ortho-para director. So here we get the ortho product and the para product. We get so little of the meta, we essentially ignore it. Why is there this ortho-para selectivity? Well, it has to do with the intermediate carbocation formed. And if we direct the incoming substituent to the ortho position or the para position, we end up with 4 resonance structures because we can move that positive charge around the ring to where it's on the carbon directly bonded to the oxygen, and then that oxygen can participate in the resonance. However, if the substituent is directed to the meta position, we only get 3 resonance structures because no matter how you move electrons around, it will never get to the carbon bonded to the oxygen. So the oxygen lone pair will not contribute to the resonance stabilization if the incoming substituent is attached at the meta position. The more resonance structures you can draw for something, the more stable it is. So the reason this is ortho-para directing is that the resulting carbocation intermediates are more stable than that would arise from a meta attack. In contrast to ortho-para directors, we also have meta directors. So meta directors either have a partial or full positive charge on the atom directly bonded to the ring. And here are some examples of meta directors. So we've got the NO2 group, which if you draw out, you will see that there's a positive charge on the nitrogen. NR3 group, so a nitrogen with 3 alkyl groups attached, it would also have a positive charge. So these would be attached to a benzene ring or some other aromatic ring. C triple bond N, cyano group. So the carbon doesn't have a formal positive charge, but nitrogen's a lot more electronegative than carbon, so it will have a partial positive. SO3H. Oxygen is going to pull electron density away from that sulfur, so there's going to be a partial positive on the sulfur atom. And then all of my carbonyl groups and derivatives have a partial positive on that carbon because oxygen is much more electronegative than carbon. So here we have nitrobenzene. This group is a meta director. So the primary product we get is the incoming NO2 group at the meta position. we get very little of the ortho and para, so little that we just ignore those. So why are these group meta directors? To figure this out, just like with the ortho-para, we need to draw all of the different carbocation intermediates that can result. So with the ortho and para attack, we get a very unstable carbocation intermediate where the positive charge is right next to the nitrogen atom that already has a positive charge on it. So positive charges do not want to be on atoms right next to each other. So that is destabilizing. However, if instead we only do a meta attack, we never get the positive charge on the carbon right next to the positively charged nitrogen. So this is better. So this is destabilizing. So just like with the ortho-para example, we get the type of attack, ortho-para versus meta, that results in the most stable carbocation intermediates. What about the effects of these substituents on reactivity? Meaning, how fast would a benzene ring with a particular substituent react with an electrophile? So if we have benzene as our standard, our baseline, we call that 1. If we add an OH group to make a phenol, that's 1,000 times more reactive than just plain old benzene. However, if we add a halogen, that is much less reactive, and then if we add a nitro group, that is significantly less reactive. So the key here is whether the substituent adds or takes away electron density from the benzene ring, because the benzene ring is acting as a nucleophile. So the more electron density it has, the faster it will react. The less electron density, the slower it will react. And halogens withdraw electron density, and then any type of positively or electron deficient substituent will also decrease the electron density of the ring. Activating groups contribute electrons to the aromatic ring, and deactivating groups withdraw electrons from the aromatic ring. There are two origins of substituent effects, the inductive effect and resonance effects. In the inductive effect, electrons are donated or withdrawn through sigma bonds due to differences in electronegativity. So in all of these examples shown here, the atom directly bonded to the ring is either more electronegative and thus shifting electrons towards itself, or it is partially positive, such as these carbons, and it is also therefore drawing electron density towards itself. Now, an alkyl group actually will inductively donate electrons. In the resonance effect, there's a withdrawal or donation of electrons through resonance. And for example, we can donate this pi bond to this Y atom that has a partial positive charge. And this would be analogous to a carbonyl or a nitrile group or an NO2 group. So by doing that, you get a formal positive charge on the aromatic ring, thus decreasing the electron density in the aromatic ring. So understanding about substituents that activate versus deactivate the ring, can you now explain why Friedel-Crafts alkylations typically give polyalkylation, but the acylations do not? Put your thoughts in the chat. And then this is just a table summarizing meta-directors and ortho-para directors. So notice that the meta-directors are all deactivators, but with the ortho-para directors, some are deactivators and most are activators. So the halogens are ortho-para directors because they have a lone pair. So if there's a lone pair on the atom directly bonded to the ring, it's an ortho-para director. But because they withdraw electron density inductively, they are also deactivators. And here's another chart classifying substituent effects. We have meta-directing deactivators. Those will deactivate the ring and direct incoming substituents to the meta position. Then we have our ortho-para directors. The halogens are deactivators and the rest are activators. Now, what if you have more than one group on your benzene ring and you want to do a reaction? If both of the groups reinforce each other as to where the substituent will go, then it's pretty straightforward. So for example, the methyl group is an ortho-para director, so it will direct the incoming group to the ortho position. It can't direct it to the para position because there's something already there. And then NO2 is a meta-director, so it also directs incoming groups to the same position. So if we were to do the bromination reaction with para-nitrotoluene, the bromine would go here. And the two different directing groups reinforce each other. What if they don't reinforce each other, but they actually oppose each other? Well, in that case, the more powerful activating group wins out. So here we have the OH group directing here and the methyl group directing here. And the OH is a more powerful directing group, so you end up with the NO2 group here. If you're unsure of which group is more powerful of an activating group, just look at the previous slide and keep that in your notes. Another thing to mention is that when you have two groups on a ring and you want to add a third group, it's not going to go in between the two groups because it's too hindered. So here's an example. We have a di-substituted benzene ring, and you need to figure out at which position will electrophilic substitution occur. So if we're going to add an electrophile to this, where would it go? Here, 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 or here? Or at a combination of those spots. So pause the video and see if you can figure this out on your own, and then resume the video for the answer. So both groups are ortho-para directors. So first of all, we're not going to direct the incoming electrophile there because it's too hindered. The OCH3 will want to direct the electrophile at this position, ortho to it and para, and the bromine will want to direct the incoming electrophile also to those two positions. So this is a case where the two substituents reinforce each other. So we're going to get these two products where the electrophile is ortho to the OCH3 and para to the bromine, and the second product where it's ortho to the bromine and para to the OCH3. Attack does not occur between the two groups because that is too hindered. Now let's